Hello again and welcome back to chemistry. Today's lesson is going to be on buffers and titration. The targets we're going to look at is understanding how the components of a buffer solution, what they are required to be, and explain how they're able to resist changes in pH by reacting with the different components, to calculate the pH of a buffer solution, and to describe how to choose appropriate reagents to prepare a buffer of a given pH. We're going to start off with predominantly learning how to compare the components and then to calculate the pH as a buffer solution is prepared and used up. So we're going to start off with exercise 1 here. It's the pH of a buffered solution 1. We have 1 liter of a buffered solution contains 0.5 molar acetic acid and 0.5 molar sodium acetate. We want to calculate the pH. A buffered solution is always going to be a combination of a weak acid plus its conjugate base salt, or a weak base plus its conjugate acid salt. So we're always going to have a combination of those two things in order to generate a buffer. Our first scenario here, we have an acetic acid. We're always going to start off by writing the equilibrium system for the either weak acid or the weak base. So we have acetic acid plus water yields hydronium ion and acetate ion. And a buffer is what's part of a type of reaction known as the common ion effect. So we have both some of our acetic acid, we have 0.5 molar here, and some of our sodium acetate. And since we have sodium acetate, this is a very soluble salt. The sodium is going to be acting as a spectator ion, and then will no longer be part of our original reaction. I'm also going to go ahead and set up my Ka expression because it's just good practice to do so. At this point you might not need it, but it never hurts. Okay, here we've got the water. We can just mark out because its concentration is not going to change with any significance and is not part of the K expression. Initially we're going to assume that we have no hydronium, and that gives us the added benefit of not having to set up a reaction quotient expression to figure out which way the reaction goes. So it's going to progress to the right because we do have to have some hydronium. So we'll add plus x and plus x on the right, 1-to-1 ratios there. So then my equilibrium is going to be 0.5 minus x, x, and 0.5 plus x in terms of concentrations. Then I can go back in and I can plug into my Ka expression. And I have 1.8 times 10 to the minus 5 equals x times 0.5 plus x and 0.5 minus x. I learned a new rule instead of the 5% rule where you have to check it afterwards. Actually somebody on one of the videos taught me this and I was really grateful. The 500 rule, you take the concentration, initial concentration, divided by the K value, and as long as that value is greater than 500, then your initial concentration is not going to be appreciably changed. In our case, we have 27,777. That is definitely greater than 500. And what that tells me then is that I can neglect the x that's being subtracted or being added. So I can mark these out. This is an excellent one, and you'll find this when you have equal concentrations of acid and salt, or base and salt, that you have the same value here. So those will cancel, and x is equal to 1.8 times 10 to the minus 5th molar, which is also equal to the hydrogen concentration, or hydronium. And so to get the pH, I take the negative log of my hydrogen concentration, and that gives me 4.74. So my initial buffer solution has a pH of 4.74. The next part of this, we're going to alter the buffer solution. I'm going to add something to it, which is going to require me to do something new. It says calculate the change in pH that occurs when a 0.01 moles of solid NaOH is added to 1 liter of the solution above. First, use the acid-base reaction and stoichiometry to determine the new concentrations of this represents the acid and this represents the conjugate base salt. So to do this, the acid-base reaction that we have here is we have sodium hydroxide, and if we consider the parts of the buffer, we have to decide is the base going to react with the acid, or is the base going to react with the conjugate base? So the smart thing to do here is to say acid-base reaction, right? So we have sodium hydroxide for our base, we have acetic acid, and then this is a true acid-base neutralization. So this is a forward progressing reaction. It goes to completion. It's going to use up all of the strong base that's available to make water and sodium acetate. You can also write this equation as a net ionic equation if you would prefer. Just using the hydroxide ion plus the acetic acid makes H2O and then C2H3O2 minus acetate ion. Here's where we're going to learn something new. We're going to learn a new kind of chart. We have to figure out all of these concentrations before the reaction and after the reaction. So we're going to do something that's a little bit different. It looks a lot like a rice table, but it's not. It's before, C is still change, and then after. The difference in a BCA chart and a rice table is that now we have to use the number of moles rather than molarity. So this is a huge important difference between these two things. The NaOH, it already gives us the number of moles is 0.01, so that's quite helpful. The acetic acid we're bringing down from the previous question. We had 0.5 moles per liter, and the question tells me that I have 1 liter of this substance. So that tells me then that I have 0.5 moles of acetic acid. Water is irrelevant, and then we do the same procedure for the acetate ion from the above table. We start off with 0.5 moles per liter times 1 liter gives me that I have 0.5 moles. Now the change that occurs is going to be driven by the sodium hydroxide right here. This is the driving force, the strong base reacting with the acid. That implies, based on what I've got here, I've got just a little sodium hydroxide, but I've got a lot of acid, or at least relatively. That means that I'm going to use up, this is kind of like a limiting reactant problem, I'm going to use up all of this strong base reacting with this acid. So on the reactant side, it's going to be minus 0.01, and then on the product side, it's going to be plus 0.01 moles. So that means afterward, I'm going to have no sodium hydroxide left. I'm going to have 0.49 moles of acetic acid left. Water is still irrelevant. And I'll have 0.51 moles of acetate ion left. I also drew a bracket here, which hopefully you guys remember this represents concentration. So to find this, we take the after divided by the total volume in case the volume changed. So 0 divided by 1 liter is still 0 molar. 0.49 divided by 1 liter is 0.49 molar. And 0.51 divided by 1 liter is 0.51 molar. So this gets me what I'm asking for in this part of the question. Determine the new concentrations of acid and conjugate base. So those are my new concentrations for part A. For part B, it says, second, use weak acid equilibrium and rice to calculate the new pH. So this, back to the acetic acid, is our weak acid equilibria again. So we're back to an equilibrium situation, double arrows. All right, and I'm going to bring down my values from above and generate a new rice table. Again, we're assuming that we don't have any hydronium here because what was happening before was a neutralization reaction, so it was creating water, not hydronium. And then 0.51 molar here. So again, we're back to molarity. BCA chart, number of moles, rice table, molarity. Okay, so minus x, plus x, plus x, 0.49 minus x, x, and 0.51 plus x. We're still talking about acetic acid, so we have the same Ka situation. 1.8 times 10 to the minus 5 equals x times 0.51 plus x over 0.49 minus x. All right, again, we're going to check out that 500 rule. I suspect that we should not have any challenge with it since it was so large last time. Yep, it hasn't changed by much. It's still 27,000 something. Is greater than 500. So we can drop the x. So I'm going to go ahead and mark these off and then solve for x. So 1.8 times 10 to the negative 5 times 0.49 and then divided by 0.51. X equals 1.729 times 10 to the negative 5, and then the pH would be our negative log of that. Is 4.76. So we see that the pH changed slightly, but not considerably, considering we added some very strong base to it. Then the last part, okay, compare this pH change with that which occurs when 0.01 moles of solid NaOH is added to 1 liter of water. So now we don't have a buffered situation. Now we just have a situation where we have a hydroxide concentration that is 1 times 10 to the minus 2 molar. So that means that the POH is equal to 2. And then the pH is 14 minus the POH. So the pH is equal to 12. So you can see that even though that was not a lot of NaOH, that has a considerable effect on the overall pH of the system. So there's your first buffer system problem. Good luck. See me if you have questions.